Hello, welcome to another module in this massive open online course. So, we are looking at example problems related to matrices and convex sets. Let us continue our discussion. So, we are looking at example problems. In particular, in the previous module, we started looking at the properties of norms, correct? In particular, we have seen that for instance, the L2 norm is greater than the L infinity norm. Now, in the same vein, one can also show that the L1 norm for a vector is greater than or equal to the L2 norm. Okay, and this can be shown simply as follows. If you look at the L1 norm, that is simply for an n dimensional vector, the sum of the absolute values of the magnitudes, that is what we have seen, that is the L1 norm. Okay. And if you look at the square of the L1 norm, the square of this quantity, that is simply magnitude x1 plus magnitude x2 plus magnitude xn whole square, which you can expand as follows, which is basically, well, it is magnitude x1 square plus magnitude x2 square plus so on magnitude xn square plus summation over all combinations of I comma j, the product magnitude xi into magnitude xj. Now, this quantity, this products, cross products, the sum of all cross products, this is greater than or equal to 0, because the magnitudes are positive, implies that this is greater than or equal to magnitude x1 square plus magnitude x2 square plus magnitude xn square, and this is nothing but the 2 norm square, norm x2 bar square. So, we basically have, what we have is that norm x bar, the 1 norm square is greater than or equal to the 2 norm square, and therefore, this implies both these quantities are positive, the square of one is greater than the square of the other. This means the 1 norm is greater than or equal to the 2 norm. And we had already seen that the 2 norm is greater than the infinity norm, therefore, putting all these things together, you have the 1 norm is greater than or equal to the 2 norm is greater than or equal to the infinity norm. This is the result that we have. The 1 norm of a vector is greater than or equal to the 2 norm is greater than or equal to the infinity norm. The 1 norm is the sum of the magnitude values of the elements. The 2 norm is, you can think of this as the length, the Euclidean, the length of the vector in Euclidean space, and the infinity norm is the maximum value of the magnitudes of the different elements of the vector. Okay, so these are the different norms. Okay. Let us continue our discussion. Now, let us move on to look at example problems related to convex sets and their applications. Alright, so we have defined convex sets, looked at their properties. Let us do some example problems to understand these things better. Okay, so what we want to look at next is convex sets. We want to explore different types of convex sets, their definition, classification, and so on. Okay. Now, for instance, let us start with the first problem. Problem number, let us call this as problem number, the previous one as problem number, we had this, let us call this as problem number So, we had problem number I think 6. So, let us call this as problem number 5, 6. So, let us call this as problem number 7. I think we can start problem number, or let us forget this, we can start problem number 7 over here. Let us call this as problem number 7. And what we want to show is the set of, let us say we consider 2 vectors or 2 points in n dimensional space denoted by the vectors a bar and the vector b bar, and we want to find, so these are 2 points in n dimensional space. Okay. These are all points, 2 points in n dimensional space. Now, we want to find the points, set of points closer to a bar set of points that are closer to a bar than b bar, and what we want to see is, if we call this set S, we want to show, we want to find is S convex, is this set S of all points which are closer to a bar, that is, if we have 2 points in n dimensional space a bar and b bar, is the set of points x bar which are closer to a bar, right, than b bar, is this set of points convex. That is, if you look at the set of points, the distance of any point x bar between a bar, we know that distance is the 2 norm of x bar minus a bar, and the distance to b bar is norm, the 2 norm x bar minus b bar. We want to see what is x bar belongs to this set if this distance, that is this distance to a bar is less than or equal to distance to now. Is this set convex? Well, this implies that norm x bar minus a bar whole square less than or equal to norm x bar minus b bar whole square. Now, remember, the norm square of a vector is a vector transpose times itself. This implies norm x bar minus a bar transpose norm x bar minus b bar less than or equal to, or norm x bar minus a bar vector transpose times itself is less than or equal to norm x bar minus b bar transpose norm x bar minus b bar. This implies that, now if you split this or if you expand this, this will be x bar transpose x bar minus a bar transpose x bar transpose a bar. Now, since they are scalar, a bar transpose x bar and x bar transpose a bar are the same. So, this will be minus 2 x bar transpose a bar plus a bar transpose a bar less than or equal to, again the same thing, similar, x bar transpose a bar minus 2, I can also write it as b bar transpose x bar transpose b bar or b bar transpose x bar, both are same, plus b bar transpose b bar. And now you can see x bar transpose x bar transpose x bar cancels. This implies that if I bring the b bar over the other side, this implies, let us write this as a bar transpose x bar, both of them are same, x bar transpose a bar. Note that a bar transpose x bar equals, because it is a number, a bar transpose x bar transpose, which is equal to x bar transpose a bar, because it is a number, it is a scalar quantity. So, this implies b bar minus a bar transpose times x bar less than or equal to, well, b bar transpose b bar, that is your norm b bar square, or there is a 2 factor of 2 here, minus norm a bar square which implies that B bar minus A bar transpose X bar less than or equal to half norm B bar square minus norm A bar square, and therefore, if you call this as if you call this vector as C bar, B bar minus A bar, if you denote it by C bar, and if you denote this quantity by D, that is your C bar equals B bar minus A bar, and this constant D equals half norm B bar square minus norm A bar square. We have an equation of the form C bar transpose X bar less than or equal to, well, D, and if you look at this, this is nothing but the equation of a half space. Alright, C bar transpose X bar into equals D bar, that is a hyperplane, and C bar transpose X bar less than equal to D, some constant D, that is a half space. So, this set of all points X bar which are closer to A bar than B bar represents half space, and therefore, the set is convex. That completes the proof. So, if you look at this set, it represents a half space, implies this is convex. And interestingly, if you look at that, if you are wondering what that set is, if you look at these points A bar and B bar and the line joining these points A bar, B bar, and if you look at the perpendicular bisector of this, okay, if you look at the perpendicular bisector of the line joining A bar, B bar, all the points that are closer to A bar than B bar lie on basically one side of this perpendicular bisector, and this is the half space that you are talking about. Essentially, this is the set of all points closer to A bar. This is the set of all points that are closer to A bar than B bar, and therefore, this is equal to a this is indeed, you can see clearly, this is a half space. This is a set of all points, that is, if we look at the perpendicular bisector of the line joining A bar and B bar, this is the half space that lies towards A bar. This is the half space, that is, the perpendicular bisector divides A bar, divides it into two half spaces. The half space that includes A bar, that is the set of all points which are closer to A bar than B bar, which is indeed a half space, and therefore, it is indeed convex. Okay. So, that basically completes the proof. Of course, we have proved it analytically, and that should leave no question, and this is basically an insight into the convex set. Okay. Let us look at another problem. Let us look at another interesting set. So, we have S equals the set of vectors x bar, so set of two dimensional vectors x bar equals x1 x2 such that x1 x2 greater than or equal to 1, and we want to ask the question again, is S convex? Is this set S convex? Now, if we look at this two dimensional plane, okay, if we plot x1 equals x2, that will be this hyperbola, correct, x1 equals x2 or x1 x2 equals 1, and of course, we are considering the positive. Let us also maintain that, let us also impose this additional constraint x1 greater than or equal to 0, x2 greater than or equal to 0. Okay. And now if you look at this, so this is your x1, this is your x2, and x1 x2 greater than or equal to 1, that includes this set. Okay. So this is the set of all points such that x1 x2 greater than or equal to 1, and you can see visually see that this is convex. We are going to take an alternative approach. What we are going to show is that this this convex set can be represented as the intersection of an infinite number of half spaces, and since it is the intersection of half spaces, it is essentially a polyhedra. It is an infinite number of half spaces. It is essentially a convex set because it is the intersection of several convex sets that are half spaces basically. So, and you can clearly see that if you draw the tangent and if you look at the corresponding half space, okay, and if you draw all such tangents, the infinite number of tangents, you can represent this as the intersection of an infinite number of such half spaces. Now, let us look at any point, well, where x1 equal to alpha implies x1 x2 equal to 1. So, x2 equals 1 minus alpha. So, we are considering any point, consider any point. So, let us start with this. Consider a point x1 equals alpha, this implies x2 equals 1 over alpha, since x1 into x2 equals 1. So, we consider this point alpha comma 1 over alpha with alpha greater than 0. And now, if you look at this quantity dy by dx, dx2 by dx1, that is, if you look at the tangent to the curve, if you look at the slope of the tangent, so this is your tangent, and the slope of the tangent to the curve equals dx2 by dx1, that is, at that point the tangent has the same slope as the curve. So, dx2 by dx1, which is, remember, x2 equals 1 over x1, which implies dx2 over dx1 is minus derivative of x2, that is 1 over x1 with respect to x1 is minus 1 over x1 square, and at this point evaluated at x1 equals alpha. So, this will be minus 1 over alpha 1 square, and so this minus 1 over alpha square, what is this? This is basically the slope of the tangent. Why is this the slope of the tangent? At that point alpha 1 over alpha, at that point x1 comma x2, if you look at the derivative, correct, if you look at the derivative of the curve, that itself gives the slope of the tangent. Okay. And therefore, we have the slope and we have the point. The point is 1 over alpha and the slope equals minus 1 over alpha square. So, the tangent will be point through alpha 1 over alpha with slope minus 1 over alpha square. So, that will be given as, well, x2 minus 1 over alpha divided by x1 minus alpha. The slope is nothing but difference of the y coordinates by difference of the x coordinates. So, x2 minus 1 over alpha divided by x1 over alpha equals minus 1 over alpha square. This implies x2 minus 1 over alpha equals minus 1 over alpha square x1 minus alpha. This implies alpha square x2 minus alpha equals Well, minus x1 plus alpha, this implies, if you can see this, this implies alpha square x2 plus x1 equals 2 alpha. Okay. So, this is the tangent to this curve x1 x2 equal to 1 at alpha comma 1 over alpha, tangent okay. So, basically what we have is you have this curve x1 x2 equal to 1 and you have this particular tangent, you have this half space. Now, you take all such tangents and you take the intersection of these half spaces, okay, and what you will see, you will end up getting this original convex set. So, the set x1 x2, so if you look at the set x1, that is x bar, such that x1 x2 greater than or equal to 1 comma x1 greater than or equal to 0, x2 greater than or equal to 0. If you look at this set, this set is equivalent to the set, that is, this set is equal to the intersection of all the sets. Intersection over what? Intersection over any point alpha greater than 0 such that x bar such that alpha square x2 plus x1 greater than or equal to 2 alpha. Okay. So, this is alpha square x2 plus x1 equal to 2 alpha, this is the tangent, which implies alpha square x2 plus x1 greater than or equal to 2 alpha, this is the half space. Okay. So, this convex set x1 x2 greater than or equal to 1, this is the intersection of all these half spaces, the intersection of an infinite number of half spaces. Implies this is convex. So, the set x1 x2 greater than or equal to 1, we have represented that as the intersection of an infinite number of half spaces, and therefore, indeed it is a convex set. Alright, so these are interesting applications, interesting problems which demonstrate, which show you how to demonstrate the convexity of a set and how to visualize the different properties or the different aspects of a convex set. Alright, so we will stop here and continue in the subsequent modules. Thank you.